Let's see how to solve topological sort using Kahn's algorithm. Okay. Kahn's algorithm is simply like solving the topological sort using BFS, and let's see how can we do that. Let's see this with an example. Okay. So let's take this example. So this is a directed graph, and there is no cycle in this. So topological sort can be applied only to directed acyclic graphs. Okay. So what I'll do is first I'll mark uh, in degree of all the nodes. Okay, that's right. For 5 it is 0, for 4 0, 0, 2, 1, 2, 3, 1, 2, 1. Okay, I have written the in degrees. This is the first step. So second step is hmm, first step, calculate in degree of every node. The second step, add nodes with in degree to a queue. Okay, let's see. This is my queue, and I'll check all the nodes whether it has in degree 0 or not. 2 no, 1 no, 3 no, 2 no. For 5 and 4 it is 0, so I'll add that 4 comma 5. Okay, so what is my next step is I'll take a result. So this will store the nodes in order. This will give my result. This will show my result. Okay, so add nodes with integrate to a queue. Next, um, like pop the first element, pop each element from queue. Okay, and add it to result. After that, within this step, after adding it to result, check its neighbors. Check its neighbors and um, decrement the neighbors in degree by 1. So I'll tell you why I'm doing this. So the reason is, so right now what we need to do, pop each element from queue and add it to result. What is the first one? 4. Okay, I'll pop it. So I'm popping 4, I'm adding it to result. Still here it is okay. So I need to decrement its neighbors in degree by 1. So uh, let me explain why I am doing that. So in topological, so what we need uh, order of all the nodes. That means if there is an edge between A to B, A should be first, then we can have B, like somewhere. Okay. So right now here 4 should be before 0 and 5 should be before 0. What I'm doing, I'm adding 4 to my result. So for 0 to be in the result, 5 and 4 should be before 0. I'm adding 4 to my result. That means out of the two nodes, I have added already one node. That's why I'm decreasing this count to uh, what? So 1. Okay. So the same. And what are the other neighbors? Another one is 2. All the neighbors, decrement them by 1. So this you will do. And what will the first step? Fourth step is decrement them by 1. So if neighbor in degree becomes 0, add it to queue. Okay, so I'll explain why. Let's see the next example. So 4 is done. Um, so I'll check its neighbors 1 and 1. Are they in degree of 0 is 1, it is not 0. In degree of 1 is 1, it is not 0. Next I will check q. What is the element? 5. Okay, I'll pop it. And I'll add it to my result. Okay, and I'll check its neighbors. What are the neighbors of 0? 0 and 1, 0 and 2. I'll decrement their in degree by 1. Okay, so decrementing this, degree becomes 0. So if in degree if neighbor in degree becomes 0, add it to result. So why I'm doing that, because right now I got 0 in degree as 0. That is because 4 and 5 are 4 and 5 should come before 0. I have added them to the result. That's why it's in degree reduced to 0. So there are now I can freely add 0 to the result, because all the requirement that need to come before 0 has already added. So it is 0. I'll add it to 0, and sorry, my bad. Add it to okay, q first, because there may be some other nodes that are connecting to 0. Okay, add it to q, not result. Okay, sorry for that. Similarly, what is other neighbor? It is 2. Make it reduce it to it is 0. So similarly, add it here. So this is done. Next, I'll check 0. I'll pop 0 and check its neighbors. I have popped 0. I have added it to queue. Add it to result and check its neighbor. There are no neighbors, so we can go to the next element in the queue. So I'll pop the next element, which is 2. Add it to result, and now check its neighbors. What are the neighbors of 2? Only 3. Decrement its indicate by 0. So and it is 3. I mean it became 0. So add it to q. 3 in degree 0, so add it to q. Okay. So now let's again pop 3 and add it to result, and check 3 neighbors. What are the 3 neighbors? Which is only 1, and decrement its indicate to 0. It became 0. So add it to q. So check 0 neighbors. Now 3 neighbors are all done. Now we have 0 in the queue. Sorry, my bad. It is 1. 1 in the queue. I'll pop it and check its neighbors. I'll pop 1, add it to result, and checking its neighbors. Are there any neighbors? No, there are no neighbors. And the queue is empty. We can stop the process, and we got our result. We can return this. Okay. Let's see how can you write code for this. So what are we doing? We need a result. What do we need first? A result. And a queue to show the vertices. A normal queue will be enough. So, and then we need to show the integers. This would be enough. Now let's okay, do we have adjacency list? No, they have given us edges. We need to form adjacency list. Let's form more thing. Next, I'll iterate through all the edges. So if it is 3, 0, that means there is a directed edge from 3 to 0. Okay. Data of u dot add of u. Okay. This is done. So I got my adjacency list. So what next? Now I need to add all the nodes which has in degree 0 to the queue. First of all, I need to calculate in degree. Okay, which I forgot. So how can we get it? It's simple. Like I'll tell you how. Let's see the adjacency list for the given one. So this is 0th index. So from 0, there is no direct edges. From 1, there is, it is a to 0. This is for 2. From 2 again it is a to 0. From 3 to 0. Okay, I'll come here, I'll check what are the edges within. This is for 0, 1, 2, 3. From 0 it is no, there is no edge to any node. Okay, from 1 there is an edge to uh, node 0. That means in degree of 0 in degree will be 1. Okay, I'll come here again, there is an edge from 2 to 0. So 0 is another getting another edge to be, so it is 2. Similarly for here it, after that it will be 3. So 0 in degree is 3, all the other in degrees are 0. Okay, here you can see there are 3 edges to 0. That's how we can calculate. You just need to iterate through its instances. That's it. Current I0 less than V I plus I thought essentially start get off by in degree of naive plus plus. Okay, so this is done. We need to store the nodes which has in degree 0, because they are not dependent on any other nodes. If in degree of I equal to 0, add it to Q. Okay, so now well, Q is not empty. I'm going inside. Okay, so it is not empty. I'll pop it. And current node will be Q dot pole. Okay, I'll add it to result. Add of current node. I'll check its neighbors. So, and I'll decrement its neighbor in degree of neighbor minus minus. Okay, after decrementing, if the in degree is 0, in degree of neighbor is 0, that means it got all these dependent edges stored in result. So now it can be added to result. Okay, that means in degree is 0, so I'll add Q dot add of neighbor. Okay, and that's how the process continues. At the end, we can return the result. Let's see. We're getting, is there any errors? We got some errors, so it should be in degree here. So let's try to submit this. Okay, it got accepted. Let's analyze time and space. So time will be so I'll be avoiding calculation for adjacency list. If you want, you can add that. So time will be this is big of V, calculating in degree and adding nodes of in degree 0 to Q. This is big of V. Okay, two big of V's, and we know this is we are applying BFS using the Q data structure here. So this is the dielectric graph. So it is big of E. We'll go through all the edges at most once. Okay. Space will be, this will be big of V, again big of V at max. Q will store in degree big of V. So big of 3V. That's about time and space complexity. Thank you.